If you're in university and have studied differential equations, you've mostly worked with linear systems and have not seen a lot of examples of nonlinear differential equations. You probably know how to solve an equation like this or this, but haven't seen a lot of equations like this, or systems of differential equations like this. This is because linear systems are easier to solve and study, but nonlinear systems are not. Well, a natural question to ask is why even study nonlinear systems? It's because most of nature is nonlinear, and although they're pretty hard to study locally and solve for their solutions explicitly, it's much easier to study their global behavior. Another distinction is that linear systems' behavior does not change regardless of initial conditions and varying parameters, but nonlinear systems can behave differently depending on these factors. I'm going to use the Lotka-Volterra predator-prey model as an example to show that nonlinear differential equations are in fact in play in nature. This is a simple model showing how the population of predator, namely the lynx, and a prey, namely the hare, changes throughout time, considering that they're the main factor changing the population of one another. We're going to model the following system using H as the population of hare and L as the population of lynx. And then we ask, what is the rate of the change of the population of hare with respect to time? The population is going to increase depending on the value of the population itself and an intrinsic factor alpha, which depends on things like the duration of pregnancy or how often the animals mate. Due to the fact that they're being hunted, their population is going to decrease depending on factors like their own population and the population of the predators. And once again, another intrinsic factor, beta. We have a similar expression for the rate of the change of the population of the predators. However, if predators were left by themselves, they would actually decrease their population. This is due to the fact that they would starve and die. And this is why the first expression is actually negative. And they're going to increase their population depending on the value of the population itself and the population of the prey, and another intrinsic factor, delta. Throughout the video, we're going to use these values as an example to be able to follow the numbers and the calculations a little bit easier. Next, let's say we wanted to find the solution of h in terms of time. First, we need to find out what is the differential equation that only includes the terms h. We do this by decoupling the differential equation. The following differential equation is actually very difficult to solve. Using a computer, we can actually graph the solutions of the two differential equations. And although we do have periodic solutions, these are not quite sines and cosines. So what is the next thing that we need to do? Since it is difficult to study how these populations evolve throughout time, it may be easier to study how h and l change with respect to one another. One question we may immediately ask is, are there any special states to the system? One answer that you may think of is equilibrium. Equilibrium is the state in which your system is in balance and therefore would stay at that state. What does this mean mathematically? It means that derivatives are zero for equilibrium. This is a useful method for studying autonomous systems, and most of nature happens to be autonomous, which means that we can freeze time and study the system. So, as we know, equilibrium points are the points in which the population does not change, which means that our derivatives are zero. This means that we end up with two equations and two variables, and we need to find the values of h and l such that these two equations are simultaneously zero. The pair of points that we find are 0, 0 and gamma over delta, alpha over beta, or from our example earlier, 3/2 and 5/3. So, imagine h is the x-axis and l is the y-axis. If we are here, we're at an equilibrium point. If we are here, we are at an equilibrium point. However, what happens where we are here? Are we going to go closer to one of the equilibrium points, or away, or how does the population change? This is why it's useful to classify the nature of the equilibrium points. We do this by studying the points nearby the equilibrium points. And the method we use is called linearization. Now, I'm going to get into the nitty-gritty of the mathematics a little bit, so just bear with me. First, we're going to use the vector x, at which all of its entries are the variables that are present in our problem. For our model of Lotka-Volterra, it's just HL. F is just all of the expressions on the right-hand side of the equation. For our model is this, and using the numbers from our example, we end up with this vector. And so, this is our system of equations. So how do we solve this? As the name might suggest, we're going to linearize the right-hand side of the equations, which means that we're going to do a Taylor expansion of the right-hand side. The zeroth order term is actually 0, and this is because we are expanding about our equilibrium points. Next, we're going to ignore all of the higher order terms, and end up with a simpler expression like this. Remember, the vector x is the vector including all of our variables, and the vector x0 is our equilibrium point. Then we do a simple transformation, replacing x minus x0 with the vector x tilde. This gives us this equation. This is much easier to solve, and if you know any linear algebra, you may be able to solve this immediately. Next is, what is this df at x0? Well, this vector is called the Jacobian, and it is evaluated at our equilibrium point. And Jacobian is a matrix including all of the right-hand side expressions and their derivatives with respect to all of our variables. Well, to understand this better, let's do the same exact thing we did with our model. Well, this is the system that we have. Running a vector notation, we get this, and our Jacobian would be this matrix. Evaluating it with numbers that we have chosen earlier, we end up with 5 minus 3l minus 3h, 2l minus 3 plus 2h as our Jacobian. Next we ask, okay, how do we solve this? If you know linear algebra, once again, you may know how to solve this. You may ask, what does the matrix A in the exponent mean? Well, a simpler expression is right here, where vi is our eigenvectors and lambda I is our eigenvalues. But if you don't know, think about this differential equation. The solution is just the exponential. And how does mu affect the solution? If mu is positive, makes the system grow and diverge. If mu is negative, makes the system decay and converge. If mu is purely imaginary, makes the system oscillate. And if mu is complex, it does a combination of oscillation, and depending on whether the real part is positive or negative, it would grow or decay. Now, if you have a matrix, it just means that the eigenvalues dictate the behavior, and eigenvectors dictate the direction in which they do that. First, let's evaluate our Jacobian at our first equilibrium point, 0, 0. Putting the numbers from our example earlier, we end up with the matrix 5, 0, 0, negative 3. Finding our eigenvalues and eigenvectors, we get a positive eigenvalue in the direction of 1, 0, and a negative eigenvalue in the direction of 0, 1. This makes it so that the vector field points away from the origin in the h direction, or the 1, 0 direction, and towards the L direction, or the direction of 0, 1. This makes 0, 0 the saddle point. We're going to do the same thing for our other equilibrium point. Ending up with imaginary eigenvalues, we ask the question, what do these mean? This means that our solution is going to oscillate. Looking at a phase space diagram of L versus H, we can see that the populations oscillate back and forth in favor of hare and lynx, or in other words, our prey and predator. To understand this better, think about starting with a normal prey population. The preys get hunted by the predators, therefore their population decreases. There's less food for the predators, so now the predator population decreases. Since there's less predators, the prey population has the chance to increase, and once the population of the prey increases, the predators can now hunt them easier, and then the population of the predator increases. And because there's more predators, now the population of the prey increases, and we are back at our cycle again. To understand the general behavior of any two-dimensional system, we start with the matrix A. This is just our Jacobian evaluated at our equilibrium point. Therefore, the entries A, B, C, and D are just numbers. We then are going to find our eigenvalues. Doing so, we end up with the following expression. We then replace A plus D with trace of A, and AD minus BC with determinant of A, ending up with lambda, or our eigenvalues, with the following expression. If the expression under the square root is positive, we have completely real eigenvalues. If it's negative, we have imaginary or complex eigenvalues. And if it is 0, we have one root. The following diagram depicts all of the behaviors that a two-dimensional system could have around any of its equilibrium points. The parabola represents the line such that the trace of a squared minus 4 times the determinant, or the expression under our square root from the last slide, is 0. We can see that above it, we have oscillatory behavior. Below it, we have sources and sinks and saddle points, and on it we have degenerate sources and sinks. In the Lotka-Volterra model, we saw an example of the saddle point, which was our origin, and center, which was our other equilibrium point. So, to summarize, to understand the behavior of nonlinear systems, first we find the equilibrium points. These are the points in which our system is stable when it's at those points. Then, we linearize the system, or calculate the Jacobian. This helps us be able to figure out how nearby points are going to evolve. And then we're going to find the eigenvalues and eigenvectors. The eigenvectors tells us in which direction the nearby points are going to evolve, and eigenvalues tell us how. I hope you found this video helpful in showing how we can understand the general behavior of nonlinear systems a little bit better. In the future, I'll be making more videos on this topic and discussing the different properties of nonlinear systems, some of which are not necessarily present in linear systems, like bifurcation.